post information on the slide, so you can also use it. So we do research with our Sharing Institute, and our motivation is the environment. And what we focus on is to understand the physical basics, the chemical basics of processes there. And I represent work of Markus Ammer's research group that I'm a member of. And I'm particularly thankful to the work from Markus Ammer, Markus Lampemäki, and Adela Further, because those were the one who did all the work that I will present now. Funding is with this National Science Foundation. So we have heard a lot about water, and also ice is quite omnipresent, not only on Earth but in space. We will focus on Earth here. And for example, you have like on average 7% of the ocean is covered by ice. In winter, 50% of the northern hemisphere is covered by snow. And clouds that can be made of small ice particles can cover up to 40% of the sky. Those have large impacts on geological cycles and chemical cycles within the Earth system. For example, the Earth and snow are connected to air quality and climate change. You can have tremendous trace gas emissions from the surface. Those go to the atmosphere, change the molecular budget of trace gases there. For example, ozone. That can change the UV light that is hitting the surface. Most prominent example would be the ozone hole that develops every year over the poles. But also on the ground, we have tremendous chemistry occurring, and I will give some examples of that later. It's not only chemistry, it's also transfer of pollutants, for example. So now another motivation to study this is health issues. For example, considering that mercury is toxic and the main input of mercury to humans in the world is consumption of fish. This even led to some advisories from the EU suggesting not to consume fish for pregnant women and young children. So one question is, how does the mercury get into the fish and into the food chain? And one idea is that mercury is transported globally in the atmosphere and throughout the year deposited in snow surfaces, for example in the Arctic. And when those snow surfaces melt in spring, all the amount of mercury that has been trapped over half a year is then released within a short period to the ocean and might enter the food chain. We see similar things with organics, also toxic organics, and we see that, for example, with mountain glaciers that are retreating due to climate change. The chemistry behind that can be quite complex, so I just give you one example. For the ozone budget, let's see, O3, the ozone concentration is connected to the nitrogen monoxide and nitrogen dioxide concentrations in the atmosphere, and those might be affected by photolysis of nitrate that you find in surface snow. So much for the motivation. So what we try to study are the molecular processes, and I would like to first focus on surface absorption. So what we try is to characterize the partitioning of trace gases, chemical species, between the snow surface and the atmosphere. This has been done for decades. And what you see here is an example of acetone, and this also introduces the method that I will come back give more details later. But what you see there in this graph is kind of like this time going back. It's a spectroscopic method monitoring the acetone concentration on an ice surface, and what you see is the two carbon signals, one for the CO and one for the methyl compound of acetone. And you can see how a clean surface in the beginning, bottom line does not show these features, and then with time you see an increase that you look at the latest 3 or 4 spectra, which then stops flowing. So they have a steady state concentration on surfaces. And this is actually quite a common feature. So if you look here, what you have here is like a concentration of your specific trace gas on the surface in molecules per square centimeter. And we can relate that to the vapor pressure of that species in the gas phase. And what you see is when you increase that, you get a higher concentration on the ice, which then levels off at a certain amount, and we can parameterize that, this partitioning, which is shown in this graph, for a number of species. And this nice linear correlation shows that once we know the gaseous concentration of toxic or other trace gases, we can calculate how much is deposited on the stone surface. So far, so good. The next question is, what happens when you have water and ice, so close to the melting point? You may have snow and ice present at the same time. And what this has shown, that those transfer functions that I have shown you, they are heavily impacted by the presence of water. Not only that, also chemical reactions proceed at different speed, depending if they are only occurring in ice and snow surfaces, or if they are occurring in water-ice systems. And last but not least, we know that ice cores are also used to reconstruct global climate of the past. And once those ice cores that are drilled are exposed to water, this messes up the chronology of all those trace gases. I also showed these examples of water briefly because now we go into the details that we have been dealing with in the last few years. And this is how does actually the interaction on a molecular level between ice and trace gases happen, and is that similar to the interaction that we have in water between the trace gases and ice between those trace gases. So what we know is, if you take this as a snapshot, but you could also just take it as a picture of an ice crystal. It has a nice ordered structure. And once you move up towards the surface, you see that for the upper water molecules, the next, there are no additional water molecules to build a nice structure. So at the interface, this nice crystalline structure is disturbed. This is a common feature of all crystals. But it's particularly interested in ice because we can see this at temperatures close to the melting point, so at environmental relevant temperatures. And you see that here, that this disordered structure at the ice surface increases in thickness and also increases in its extent of disorder once you approach to the melting point. Now, the key question is, if you think of our trace gases and impurities in ice and snow, if they experience this type of structure, do they show the same chemistry and physical behavior as they do in water? Or is this still more ice-like? And we do try to probe this with the method of core electron spectroscopy. So what we do is we irradiate our sample, either water or ice, blue dot band, with photons. And this leads to the emission of electrons. There can be two types of electrons emitted. Either we go in with such high energy that we kick out core electrons, that are those close to the atomic nuclei, directly. They are emitted to the gas phase and hit our detector. Or, so this example, or we hit out the core electron, and then another electron in the valence bond replaces that one, which leads to the emission of electron from a higher layer in these molecular electrical structures. Anyway, because we are detecting electrons, and electrons do not travel very well, very far through material matter, this method is very surface sensitive. With that, we can only probe a few nanometers deep into our ice or water sample. And what we see here, so here we probe the oxygen atoms of ice and of water for comparison. And what you see is, just look at this, I mean, the water spectrum of these oxygen atoms and the ice spectrum look very different. But as you increase the temperature, you can see that the ice spectrum becomes more and more water-like. And this kind of like represents this upper layer, which becomes more and more disordered. Now, what we've been looking at is how does this water structure change when we dose, for example, nitrate, acetic acid, and acetone. So when I say dose, you have to picture this experiment. We start with a clean ice surface, and then we dose those trace gases from the gas phase. So the concentrations are very low. They cover kind of like half of this ice surface is covered by nitrate molecules, the other half is still water. And what you see is if you start with the acetone, so here you have this oxygen spectrum of clean ice, acetone and ice, and acetone gas phase. And what you see is, if you compare these two, there's hardly any difference. So, of course, you have a small increase here. That's the oxygen that we have in acetone molecules. But for the oxygens of the water molecules, the ice structure does not change, whether we have acetone on the surface or not. So the ice molecules at the surface do not recognize any acetone absorbed into it. For acetic acid, we did the same experiment, and you see when we compare the pure ice to that has acetic acid on its surface, there's a very, very small, tiny difference. Now, when we dose nitrate, that's the third one. What you see here is the pure ice spectrum in black. So there's no oxygen coming from the nitrate here, and you have the classical ice spectrum, the black line. This one is a nitrate solution at room temperature. You can probe the nitrate, you can probe the oxygen, and you get this bluish typical spectra for nitrate solution. If you now do the same experiment with the ice at 230 Kelvin, so very cold, and with a little bit of nitrate on its surface, you get one of these two curves. I don't remember which one is the experimental one. The other one is a mathematical then we try to reproduce the experimental results by taking 20% of the nitrate spectrum and 80% of the pure ice spectrum. What this shows is, once you have nitrate on the ice surface, the spectral properties of the ice surface change, and you can represent this new spectrum by taking into account the spectrum of a nitrate water solution, 20% in intensity and 80% of a pure ice. That means when you have a nitrate film on your ice surface, covering half of the surface on a molecular scale, 80% of your ice is still identical to the ice without the nitrate, and 20% is very similar to a nitrate solution at room temperature. What we can also do with this experiment is probing on how deep the nitrate goes into the ice. Because if you imagine that you have this disordered water-like layer on the ice surface, you might think nitrate is very soluble. If you would expose the water surface to nitrate, the nitrate would dilute into the whole water bulk, would diffuse through it. You would get a homogeneous distribution of nitrate in the sample. What we see on the ice is that we have different concentration. So when we probe different kinetic energy, this is shown here, this represents different probing depth of our instrument. And here we have the ratio of carbon to oxygen, indicating the concentration of our dopant. And what we see then is, these are our measurements for different experiments, that we have a depth dependence of our concentration. And when we try to calculate, to simulate that, we see that the upper line would represent 0.5 nanometer, the lower line 2.5, and the one that exactly matches our experiments is 1 nanometer. And this indicates that when we expose the ice surface to atmospheric trace gases, they do not penetrate the ice deeper than about 1 nanometer. So what you can also learn from these experiments is a little bit about chemistry. And this is a key question, like we have heard acid to bases in water. So one question might be, is that similar, do they show similar behavior on ice surfaces? And we did that with acetic acid. And so we have very low, for us, very low concentration of 10 to minus 6 millibar acetic acid in the gas phase. And we do the experiment at 233 Kelvin. And if you would expose a liquid water to that concentration of acetic acid, we would get a 10 to minus 3 molar solution. And in that solution, about 1% of the acetic acid protonated, 99% would be unprotonated. From the spectral information on the ice, we see that about 60% of our acetic acid is protonated. So even though the ice surface might be very disordered, might be very liquid-like, the properties of acids are very different in water and on ice. So to summarize this a little bit, what we know since decades is that when we have an ice crystal with a perfect symmetry, that's dark blue, we have a disordered region and the ice-air interface. And the new emerging picture would be, well, it has been suspected for long that when you throw those trace gases to this layer, it would increase in intensity and impact. And our picture is more that there is the impact of those trace gases on the structure here depend very much on the type of trace gases. So for example, organics like acetone do not change the structure at all. It doesn't sit on the surface. Organic acids do change it a little bit, but only the closest molecules surrounding them. And molecules like HNO3, strong acids, they also do not change the main part of the ice structure, but also only have a huge hydration shell surrounding them, so that in presence of impurities, the ice surface is not homogeneous anymore, but shows a very heterogeneous structure. And the questions that we are dealing now with is, okay, so if the nitrate is like in a liquid solution on ice, how would that change its chemistry? And where do the water molecules come from that surround it in its hydration shell? From the core or from the surface? And how would that change the exchange of water molecules from the ice to the atmosphere? And with this, I'd like to close this presentation. Thank you for your attention.
Time for 2 short questions, please.
Then I might address the question. Thank you for this, for me, being a non-technician, very technical presentation, which I thought was brilliant, but I didn't understand too much of the technical details. Could you maybe, just for the dumber people like me, once again, maybe sum up and point out the connection to the water as it was discussed so far in this conference? I didn't really catch that. You know what I mean? Thank you very much. And sorry for my dumbness.
This picture what I have. So, I mean, basically, ice is very similar to water. It's just colder. And know that it has huge effects on health and climate and so on. And one key question is how do we understand and parameterize those things? And then, if you look, now we go to the molecular picture, and we have seen that or heard that the molecular structure of water is not absolutely understood, but of ice is even less. I mean, we know that the most part of the ice crystal is very nicely structured. But at the upper part, where all the chemistry is occurring, it's very disordered. And if you look closely, I should have plotted that. This looks like, more or less, like water. So you have a few ordered regions, and it's very, if you have a movie, it's very dynamic, just like water. So the key question is, do all these processes that we see, do they occur in this water-like layer, or do they experience more surrounding that is more structured? So the key question is how close to water is ice? Can we understand environmental chemistry by pretending that ice behaves like water, or do we need to treat it as a special matrix?
Thank you very much for the clarification.
One of the findings in our studies is that a necessary condition when ice melts to water is it goes through an easy phase. I don't know if you were here during my presentation or not, but no, okay. Then the question is not so easy to pose. I presented evidence for a phase of water that looks like ice. It has presumably, the evidence points to a structure that's similar to ice, but not the same as ice. And we found evidence that when ice melts to H2O, it must go through this phase, just the same as when water freezes to ice, it must go through that phase. And the suggestion was that at the upper level, you have this special phase of water. Now, I'm not sure, since you haven't heard the talk, I guess I can't ask you to comment on it, but I would just suggest that you think about the possibility that having this phase plus hydronium ions at the top can explain many things, and I'm not sure whether it could explain your findings or not, but I just wanted to alert you to that.
Maybe just one quick comment. So it's indeed quite common also in environmental research to call this part phase, and also to use all the parameters that we have from the water to describe this. But I'm not so much a friend of this, because whenever we look at this, and when we look at melting processes with our techniques, we see a huge jump in the properties that we're observing from this to the melted one. So I think this is still more crystalline than water. But it is a good transition state. So yes.
Thank you. I think we should close this session, and we should get back at 2 o'clock here after lunch. Thank you.